let's see how we can prove Faà di Bruno's formula. Well, the formula is proved easily using induction. Induct on n. We've already seen that the formula is true for n equals 3. Actually, it's easy to see that this is also what the formula gives for n equals 1 and 2. So I'm not going to bother about the base case. Let's just assume that we know this formula for n minus 1. So by induction hypothesis, we have f circle g n minus 1th derivative is, well, it's the sum over all partitions in pi n minus 1 f pi gx times product over b blocks of pi g size of the block x. And so we need to differentiate this. So f circle g nth derivative, well, it's the derivative of this, and so it's a derivative of a sum is the sum of the derivatives. We differentiate term wise, and so what we get is a sum over pi in pi n minus 1, and let's differentiate each term. So this term, each term is a product, and so let's first differentiate the first factor. So we need to differentiate this first factor here, f, the pith derivative, number of blocks. So that will be just the next derivative, and we do this using the chain rule. Times g prime x, and then we get product b belongs to pi g differentiated as many times as the size of the block b. Okay, and then let's differentiate the second factor. So when you differentiate the second factor, what do you get? So we'll keep the first factor as it is, f size of pi gx, and then when you differentiate the second factor, it has one factor for each block of the partition. So we differentiate each factor and add over all the blocks. So we get a sum over the blocks. So let me just write b0 for this block that I'm going to differentiate. So I'm going to differentiate the block corresponding to b0. So I get g size of b0 plus 1 x, and the remaining I keep the same. So I get product b not equal to b0 g b x. Now let's see if this differentiated expression has any relation to partitions of the set 1 to n. Now remember, in my recursive construction of partitions of n, I said you start with a partition of n minus 1 and you have two options. Either add n to that old partition as a new block, or you add n to one of the blocks of that old partition. Now this first term here actually corresponds to adding n as a new block, which is singleton, because this g prime here goes in as just a first derivative corresponding to a block of size 1. On the other hand, if you were to add n to one of the existing blocks of pi, then you would have one option for each block. So if you were to add n to the block b0, then the size of that block would go up by 1, and that's reflected in this b0 plus 1 over here. And the number of blocks doesn't change in this case, so here it remains the same. So this corresponds to the second option which we had in the construction of partitions of n. So what we got is finally just sum over pi in pi n f of the number of blocks of pi gx times summation b in pi g differentiated the size of the block b times. Okay, so this version of Faà di Bruno's theorem is not the usual one stated, Computing it involves listing out a lot of set partitions, which can be which grows very fast. It's a large number. Can we somehow collect various terms like we'd seen when we had computed the example with just third derivative? We had these coefficients like 1, 3 and 1. In order to do this, we need to be able to count certain types of set partitions. So let's go back to looking at set partitions again and try to count them. In order to collect the terms in Faà di Bruno's formula, what we want to know is the following question. How many set partitions are there with given block sizes? So, for example, let us try this. How many set partitions in pi, let us say 12 have block sizes, let us say 3, 3, 2, 2, 2. So, 2 blocks of size 3 and 3 blocks of size 2. One way to list all these set partitions is to use permutations. So, we could just take a permutation of 12. So, we have the element numbers 1 to 12. Let us rewrite them in some order. So, we will write the permutation in one line notation A1, A2, A3, A4, A5, A6, A7, A8, A9, A10, A11, A12. So, this is just a rearrangement of all the numbers from 1 to 12. How many are there? Well, we know that, right? There are 12 factorial possible such rearrangements. So, we will take a rearrangement, a permutation of the numbers 1 to 12, and we will just break it into blocks according to the sizes that we are given. So, I will draw a line here. So, I got a block of size 3, another block of size 3, another block of size 2, and that leaves me with a last block of size 2. Now, obviously here we are over counting, right? If I were to replace this permutation A1, A2, A3, A4 and so on by the permutation say A3, A2, A1, A4 and so on, I would get the same set partition. So, I am over counting, and what is the factor by which I am over counting? So, what I can do is in this permutation I could rearrange the first 3 terms. So, that gives me I am over counting by a factor of 3 factorial, which is 6. Again in this block I am over counting by a factor of 3 factorial. In this block of size 2 I am over counting by a factor of 2 factorial, over here 2 factorial and over here 2 factorial. Okay, but I claim that we are still over counting. What I could have done, for example, as I could have interchanged this block, I could have taken the permutation with A4, A5, A6 first and then A1, A2, A3. So, then what would happen is the first block would be A4, A5, A6 and the second block would be A1, A2, A3. But I already said that when we are talking about set partitions, we are just thinking of this as a collection of subsets. There is no ordering on them, and so this again would give me the same set partition. So, what I need to do is I need to also account for that, and so this interchanging these two, this gives me an overcounting factor of 2 factorial. And what about blocks of size 2? Well, there are 3 of these blocks, right? And so, I could rearrange them in 6 possible ways, and so here I get 3 factorial. So, totally the number of partitions of set partitions of set 1 to 12 with block sizes 3, 3, 2, 2, 2 is 12 factorial divided by 3 factorial squared, there is a 3 factorial and 3 factorial times 2 factorial and then 2 factorial cubed, which corresponds to these blocks of size 2, 3 factorial. So, this first thing corresponds to the blocks of size 3, and this corresponds to size 2 blocks. Okay, we can write down a formula in general. The number of set partitions pi in pi n with, okay, so it is convenient not to say what the block sizes are, but how many blocks are there of each given size. So, let us say M1 blocks of size 1, M2 blocks of size 2, and the largest block you could have is of size n. Well, there can be only one block of size n. Many of these numbers could be 0. So, in our example, where the block sizes are 3, 3, 2, 2, 2, we have M1. How many blocks of size 1? Well, none, there are no blocks of size 1. How many blocks of size 2? There are 3 blocks of size 2. How many blocks of size 3? 2 blocks of size 3, and we can go on. The remaining will be all 0. What are the constraints on these numbers M1, M2, M3? So, obviously we have M1, that is the number of blocks of size 1. So, that will take care of m elements from 1 to n. M2 blocks of size 2 will take care of 2 times M2 elements, 3M3 plus n times Mn has to add up to n. All the elements have to be in exactly one block, and so we get this. And the number of blocks, the number of set partitions pi in pi n with mi blocks of size I is given by, so we have all the permutations n factorial, then we have to take care of our overcounting. So, if we have a block of size mi, then we are overcounting by a factor of mi factorial, accounting for the rearranging of the mi blocks of size I, but within each block we can also rearrange, so that we get I factorial to the power mi. I goes from 1 to n. This is nothing but a more general version of this formula that we had derived in the case of 3, 3, 2, 2, 2, 2. So, now let us use this to rewrite Faà di Bruno's formula. So, we have the first version of Faà di Bruno's formula, and let us write this as a sum. So, now I have to take a sum not over all set partitions, but over M1 plus 2M2 plus Mn is equal to n, and these M1, M2, M3 and so on have to be non-negative integers. And then f, how many times has it to be differentiated? Well, the number of blocks of the partition pi. Now, if a partition has M1 blocks of size 1, M2 blocks of size 2 and so on, the total number of blocks is just M1 plus M2 etc. So, this is M1 plus M2 plus Mn Gx, and then we have a product of these things. So, for each block, so how many blocks do I have? So, I have blocks of size, so what I will do is I will club blocks of size 1, blocks of size 2 and so on into one factor. So, instead of writing product over blocks, I will take a product over the sizes of the blocks. So, I goes from 1 to n, and then I would take the ith derivative of x, and this has to be raised to the power mi, right. And then I need to put in front of this the total number of set partitions with M1 blocks of size 1, M2 blocks of size 2, M3 blocks of size 3. So, let us just make some space over here, n factorial divided by product over I mi factorial I factorial raised to the power mi. And this is version 2 of Faà di Bruno's formula.